For nearly 2 decades, NASA orbiters have watched a seasonal rhythm on the cliffs of Mars. Every warm season, narrow, dark streaks appear near the ridges, crawl downhill, and then fade away as winter returns. If these streaks are formed by flowing liquid water, it proves Mars hosts an active, modern water cycle. It gives us a present-day environment where microbial life could potentially survive right now. In 2015, NASA made a definitive claim based on orbital data. They announced they had found evidence of briny water flowing on these exact slopes. We currently have billions of dollars worth of robotic hardware active on the Martian surface. So why, after all this time, haven't we simply driven a rover up to the cliffs to test the water directly? The answer is a paradox of exploration. Our machines are deadlocked by orbital illusions, by mechanical limits, and a strict biological treaty that leaves the most fascinating places on Mars completely untouchable. Without a rover on site, researchers rely entirely on orbiters. These satellites carry two conflicting tools: cameras that capture sharp, high-resolution shapes, and spectrometers that read chemical makeup in low, blocky resolution. This diagram illustrates the pixel mixing problem. A dark streak might only be a few meters wide, but the spectrometer reads the chemistry in large grids. If a narrow streak sits next to a large, stable deposit of dry salt, the instrument mixes everything inside it together. The salt dominates the average, creating a false positive for liquid brines. This cross-section shows the competing theory: dry granular flow. On these steep inclines, a tiny disturbance, like morning frost turning briefly to vapor, can destabilize a delicate top layer of bright surface dust. As the dust slides downward, it strips away the bright coating to expose the dark sand underneath. This creates an optical illusion that perfectly mimics the dark, creeping stain of a liquid flow without a single drop of water involved. Because a camera hundreds of miles away only records a change in contrast, the pixels can be used to argue for both wet flows and dry dust removal. Orbital data alone cannot settle the debate. To solve the mystery, you have to touch the sand. But the extreme geography of these streaks aggressively defends against any physical approach. This animation demonstrates the angle of repose, the absolute steepest incline granular material can maintain before gravity forces it to collapse. These dark streaks only form at this dangerous threshold. If a wheeled machine tries to navigate a 35-degree slope of loose sand, traction fails instantly and the vehicle slides. Modern Mars rovers weigh around a ton. They are built with rigid wheelbases optimized for rolling across flat plains and exploring gentle craters, not for scaling crumbling cliff walls. Ordering a flagship rover onto a collapsing dune is an operational risk no space agency is willing to take. One minor slip, and a billion-dollar machine is permanently lost at the bottom of a crater. Yet, even if a rover were engineered to climb that wall safely, it is legally prohibited from trying. Rovers are assembled by humans. Despite the most rigorous cleanroom procedures on Earth, dormant terrestrial microbes inevitably survive the journey, tucked away deep inside porous seals and complex joints. This triggers strict planetary protection protocols. Any area on Mars even suspected of hosting liquid water is classified as a special region. These zones are cordoned off to prevent forward contamination. This traces back to international space treaties, drafted decades ago to ensure that human exploration does not infect alien ecosystems with our own biology. We are left in a catch-22. If the streaks actually are water, driving our contaminated rovers into them could irrevocably destroy the very Martian life we are trying to discover. Over the last several years, the scientific community has enacted a quiet reversal. Researchers have pulled back from the 2015 water claims, accepting that dry, granular flows better obey the harsh, low-pressure thermodynamics of Mars. But because we are forbidden to touch the sites, this dry consensus remains an educated inference rather than absolute on-the-ground certainty. This reveals the ultimate paradox of modern planetary science. The closer a location gets to potentially supporting life, the harder it becomes to legally and mechanically explore it. Until we can design perfectly sterile cliff-diving robots, Mars will continue to execute its seasonal magic tricks, 140 million miles away, remaining safely out of our reach.